Hey guys, I'm back with a new video. In the previous video, we learned about the maximum margin classifier. So in this video, let us learn about the support vector classifier. So as I told you in the previous video that when our points are not perfectly separable, then we can make use of a classifier called as the support vector classifier. Now let us see an example where we cannot distinctively separate two classes using the maximum margin classifier. Let me first trace an example for this. So the topic is support vector classifier. Let us say these are our hashes, so our points that are represented by hash. Then let us say we have the second class that is represented by points, so let us make use of asterisk here, so asterisks. Now here you can see that we cannot distinctively draw a line that can perfectly separate the two classes. So here in 2 dimensions, you can see we don't have a line that can perfectly separate both of our classes. So you can draw any number of lines for this example, but no line will be able to perfectly separate these two classes. So that is the problem with our maximum margin classifier. It fails in this kind of scenario. So let me write this down. Maximum margin classifier fails in this case. So for this case, we have yet another classifier that we can make use of, and that is known as the support vector classifier. So a support vector classifier is a classifier that is able to distinctively separate two classes which themselves are not perfectly separable, as in this case. So let us see how support vector classifier is able to do so. Let us first consider the case where our both classes are distinctively separable by a hyperplane. So let me clear up some space. Here let us draw the points for both our classes. So let us represent the class 1 by using hashes. And let us represent the second class using asterisks. Let me remove this one. And here let us draw the hyperplane. Let me add a hash right here. And let us draw the margins and the gap that we have in between the two margins. So let the margins be this. So this is the smallest distance between a training observation and the hyperplane, so A units. And let us take this A units on the other side of the hyperplane. So this is also A units. And let us draw our dotted lines now. Let me use light blue shade for this, and on this side of the line as well. And you can see here that the hyperplane is exactly distant half of this total length, which is 2a. So it is a distance from both these dotted lines. This is the situation of the maximum margin classifier. So what can be the problems in this case? So one of the problems is that we are having high variance in this case. Variance, as we know, means the amount by which our model varies. So if a new data point is added and our model varies a lot, then in that case we have a high value of variance. Contrary to this, if on addition or deletion of a point the model doesn't vary much, then our model has a low variance. So in this case the variance is very high. Let us understand why it is high. So variance in this case is high. So let us now replicate the same diagram and draw our points for both the classes. So this is the class 1, and then let us represent our second class points using asterisks. So here also we are having the same count of the points that we are having in the first case. So let us add a new point for class 1. So hash, let us add it here. Let me remove these 2 points so that the distribution looks exactly identical in both the diagrams. So one right here and the second one right here. Now originally in the first case you can see that our hyperplane is say at an angle of theta from the horizontal axis. Now let us draw the hyperplane for the second case. So here it will be something like this. And this will be at an angle theta 2. Let us say this is at an angle of theta 1. Now here theta 2 will be less than theta 1 in our point distribution. So this means that by adding a single point to our dataset, our maximum margin classifier deviated a lot. So it is starting to bend a little bit to the right, so you can say towards the horizontal axis, because now our theta 2 is less than theta 1. So in essence, if you add a single data point or you delete one, your maximum margin classifier tends to show a high variance. Now contrary to this, if on addition or deletion of a point the model doesn't vary much, then our model has a low variance. In the second case, we were able to draw a hyperplane, but it deviates a lot from the one that we had in the previous case, which is this one. So it varies a lot despite just adding a single data point. Our hyperplane had to change its orientation to distinctively separate the two classes in this new case. So you can see we have high variance in this case, and this we don't want because high variance can give us lower value for accuracy. So the maximum margin classifier might not always be the best possible model in cases where we are having high variance. And because of this limitation of the maximum margin classifier, it is important for us to discuss about the support vector classifier. So even if we have distinctively separable classes in case of maximum margin classifier, the support vector classifier might be a better choice sometimes over the maximum margin classifier because of high variance in case of maximum margin classifier. So in case of support vector classifier, the classifier doesn't try to distinctively and perfectly separate the two classes like we are doing in maximum margin classifier, because in the case of support vector classifier, it understands that if it does so, just like the maximum margin classifier, the variance will come out to be high. Now before we understand how support vector classifier does this separation in a way that does improve the variance, let us first understand the concept of something called as the soft margin. Now the support vector classifier is also called as the soft margin classifier. So support vector classifier, soft margin classifier, or you can even say support vector classifier. Now let us say our points of the two classes are distributed something like this. Let us add our hash points for the first class. And let us add our second class points by using asterisks. And now let us say this is our hyperplane. And let us draw our two margins. So let us say our two margins are this and say this. So all these three lines, the two dotted ones and the hyperplane, are parallel to each other just as we had in the maximum margin classifier. Here in this case you can see that we can have points that lie within the distance of the margin. So you can see within the distance 2a, we are having these 4 points that are lying within the margin, which is not possible in case of the maximum margin classifier. Contrary to maximum margin classifier, in the support vector classifier we can have points within the distance of the margin as well, because we know that in this case our points are not perfectly separable. Now these 2 points that you are seeing here, which are these 2 hash points, are on the wrong side of the margin. So let me mark them, these 2 points, right? So the 2 points that are ticked using the orange color are on the wrong side of margin. This means that these 2 hash points should have been to the left of this dotted line, but it is on the right of the dotted line, that is, it is lying within the margin. Now if we talk about this hash point, this is on the wrong side of the hyperplane. This should have been to the left of the hyperplane, right? But this is on the wrong side of hyperplane. And this asterisk which we are having within the margin is correctly classified, because all the points that are represented by asterisk lie to the right of the hyperplane. So this is correctly classified. But this one is misclassified because it is on the wrong side of the hyperplane. So let me write this down. This point is on the wrong side of the hyperplane, right? Now these 2 points that are represented by orange ticks, namely these 2 hash points, are on the wrong side of the margin. This means that they lie within the distance of the margin and not at a distance greater than or equal to the margin, which was the case in maximum margin classifier as we had discussed. So that is why we are saying that these 2 points are on the wrong side of margin. Next, this point, as you can see, is a hash point that is lying on the wrong side of the hyperplane. And why we are saying this? Because it lies to the right of the hyperplane, whereas it should be on the left side of the hyperplane, because all our hashes or all the observations of the class 1 are on the left side of hyperplane. So this one is a misclassification, right? And it is lying in the right side of the hyperplane, where all asterisks are supposed to lie. Now margin, as we know, is the shortest perpendicular distance between a data observation and the hyperplane. But then what is soft margin? Now soft margin is a bit different. It allows some of the observations to be in the wrong side, as we just saw here. Now this means that soft margin does allow some misclassifications, that is a point lying in the wrong side of the hyperplane, which is this one. So this is a misclassification, and soft margin allows this to happen in case of support vector classifiers. So in the case of support vector classifier, perfect separation for points of two classes might not always be possible. So this was all I wanted to cover in this video, where we discussed about the limitations of the maximum margin classifier and we discussed about soft margin. In the next video we will learn more about support vector classifier and we will do some analysis related to soft margin classifier. So let's catch up in the next one.